This video is brought to you by me, as usual, and my patrons. Thank you so much to my patrons. I appreciate you guys a lot. Alright, so before we actually get to implementing YOLO, we want to first get an overview and try to understand how this algorithm works. So what that means is that, first of all, we want to understand the idea behind the algorithm. Then we want to understand the model architecture in some greater depth. And then lastly, we want to also understand the loss function. Those are three critical points to understanding the implementation later on. So just briefly before that, the dataset YOLO was trained on is the Pascal Visual Object Class dataset, or just VOC dataset. And it had images of airplane, bicycle, boat, bus, bird, etc. And in total, there were 20 classes. But just a note on this is that most papers nowadays use the MS COCO dataset instead of VOC. So it's a little bit outdated, I would say. So the idea in object detection is that we have objects in an image. In this case, we have two dogs. And our goal is to correctly output bounding boxes for those two objects. And additionally, we also want to say what those objects are. So in this case, they would also say that those are dogs. And so the idea behind the YOLO algorithm is that we're going to split this image into an S by S grid. In the paper, they have S equals 7, but I'm just going to set it to 3 just for demonstration purposes. So we're going to split this into a 3 by 3 grid. So in total, we will have 9 different cells. And so the idea is that each cell will output a prediction with a corresponding bounding box. All right, so if we go back, we can see that obviously, so each dog is actually in multiple cells here. And so the question then becomes, well, we obviously just want one bounding box for each object. And so how do we make sure that only one object will be outputted for each object? And the idea is here that we will find one cell responsible for outputting that object. And the one that is responsible is the one that contains the object's midpoint. So those blue points are the midpoints, or approximately the midpoints of those two objects. So if we zoom in on this cell containing the left dog, we're gonna have this image right here. And so one thing just to keep in mind here is that each of these cells are going to have that the top left corner is 0, 0, and the bottom right is going to be 1, 1. So as we increase horizontally, we're going to increase the x coordinate. Vertically, we're going to increase the y coordinate. And so the key here is that each output and label will be relative to the cell. And also that each bounding box will have x1, y1, x2, y2 coordinates that we've talked about in previous videos. But here, we're actually going to have that the first two, x1 and y1, are just going to be x and y, which are going to be the coordinates for the object midpoint in that cell. And then the w and the h are going to be the width and the height of that object relative to the cell. Because remember, everything outputted will be relative to the cell that it is in. So let's look at this in a little bit more detail. So the x value is going to be between 0 and 1, representing how much to the right the object's midpoint is from the origin. And similarly, the y coordinate is going to be the same, just vertically. And then this is also going to be between 0 and 1. But the width here can actually be greater than 1. And this is the case if the object is wider than the cell. And for the height, this can also be greater than 1 if the object is taller than the cell. So if we just look at our image in this case, we can obviously see that the dog in this case is going to be larger than just one cell. And this means that the height is going to be greater than 1 for sure, because we need greater than 1 cell's height to accurately capture the object or the dog. So in this case, maybe we'll have something like 0.95 because the midpoint is very much to the right of the image. And in the y coordinate, it looks about center, but perhaps slightly below center, so 0.55. And then the width of the object is perhaps 0.5 of a total cell. And then the height, let's say it's about 1.5, so it's 1.5 times the cell height of one cell. So, if we output that in this case, that's going to look something like this. All right, so let's take a look at how the labels will actually look like. So we're going to have a label, and remember, this is relative to the cell. We're going to have C1, C2 up to C20, and those are for the 20 different classes in the VOC dataset. Then we're going to have a probability, PC, that there is an object in that cell. And so that's going to be 1 or 0, 1 if there's an object, 0 if there's not an object. Then we're going to have X, Y, W, H, and those are going to be for the bounding box coordinates. All right, so the predictions are going to look very similar, but we will output 2 bounding boxes instead of just 1. And so the idea here is that they will specialize to output different bounding boxes. So maybe one of those bounding boxes will output if there's a wide bounding box object, and then the other might do if it's tall. We haven't specified exactly how they will specialize, but we're hoping that they will do different kind of bounding boxes. So how the prediction will actually look like is that we're going to have, again, 20 different classes. We're going to have PC1 and PC2, and that is probability that there is an object in the first box, probability that there is an object in the second box prediction, and then we're going to have box 1 coordinates and box 2 coordinates. But note here that since we're just doing 20 different classes prediction once, we're not doing it for each bounding box. This means that a cell can only detect one object. So this is a limitation of YOLO, in that each cell can only output one object, and if you want to have multiple bounding boxes, then you would have to create a finer grid. So what that means is instead of using a 3x3, use, as they did in the paper, 7x7, but maybe you even want to do finer than that, so maybe 19 times 19 or something like that. But remember here that this is for every cell. So everything we've seen so far is for every individual cell. So the target shape for one image is going to be S by S by 25, where 20 are for the class predictions, and 1 is for the probability score, and then the remaining 4 are for the bounding boxes. The predictions are going to be very similar. For one image, we're going to have S by S by 30, and so exactly the same as the target, except we have 1 additional probability score and 4 additional bounding box predictions. All right, so let's first try to understand the model architecture and implement this in PyTorch, and then we'll come back to the loss function and implement that later on. So before looking at the model architecture, I just wanted to mention the more details of the paper. It's You Only Look Once, Unified Real-Time Object Detection by the authors Joseph Redmond, Santosh Divala, Ross Gurchik, and Ali Farhadi. I think that's how you pronounce them anyways. So if we scroll down in the paper, this is the most important part for the model. So the input is going to be 448 by 448 by 3 images. So we're going to have RGB images and 448 and height and width. And then they detail all the steps to go through. So it's first going to be a 7x7 kernel with 64 output filters with a stride of 2. And then it's going to be a max pool, 2x2 max pool with a stride of 2. And so essentially here, the stride of 2 here is going to have the image size, and the stride of 2 from the max pool, or the 2x2 stride 2 max pool, is also going to have the image size. So as we can see here, 448 becomes 224, and then 112 after that block right there. One thing that isn't mentioned here is that in the 7x7 with the stride of 2, we're going to have a padding of 3, which I calculated from making sure that this is going to be the output size. So the idea here is that we know what the output should be after, so then you can sort of recalculate what the padding should be. But I'm not going to go into that in much more detail. I've talked about it previously in when I've implemented VGG, Inception, and ResNet, and so on. But let me know if you're confused about how they got the padding. But anyways, so what they did then is that they ran it through a 3x3 kernel with 192 output filters. and then again a max pool layer to half the input. So as we can see, 112 becomes 56. And so what they used here also is a same convolution, which in the 3x3 case, if you calculate, it's going to be a padding of 1. So moving forward, I'm not going to talk about the paddings too much. They're all actually going to be same paddings. But anyways, right there afterwards, they run it through a 1x1 and 128 filters, 3x3, 256 filters, and then a 1x1 and then 3x3 again. And then they mentioned in the paper that this is inspired by the inception net. Although if you implement the inception network, they're gonna do all of those independently, and then they're gonna concatenate them. And that's sort of the idea behind inception, that we try out different kernel sizes and we then concatenate all of them. But here they're doing them sequentially, so that's a little bit different. But they do those sequentially, and then they do a max pool at the end to half the input. So again, 56 becomes 28. And then at the end here, we're going to have 502 filters, which we get for the next box. So then they do pretty much the same thing again, except now they do 1x1 kernel. Let me see if I can zoom in actually a little bit more. Yeah. So then they actually do a 3x3. Sorry. They do a 1x1 kernel, 256 filters, and then a 3x3 with 512. And then they do that in total 4 times. And then they do again 1x1, 3x3, and then a max pool. And so all of these convolutions are going to be same convolutions, and the only thing that's going to half the input is going to be the last max pool. So 28 becomes 14 from the max pool. And then they do a very similar thing, except now they use a 1x1 and then 3x3, and they do that 2 times. And then a 3x3, 1024. And lastly, they do a 3x3, 1024 filters with a stride of 2. So the stride of 2 here is going to half the input. So 14 becomes 7. And then they just do 2 additional conv layers, but they don't change anything of the input. Then they do connected layers, so fully connected layers. They take this 7x7, 1024 input. They do a linear layer to get it down to 4096 feature vector. And then they do a fully connected again, and they reshape it to become 7x7 by 30. So as you can see here, this 7x7 are going to be the S and the split size of the image. So we're going to have 7x7 grid, and then we're going to have for each cell, there's going to be a 30 vector output. Remember, those are 20 for the cells, 1 for the probability score of the first box, 4 bounding boxes for the first box, second probability score of the second box, and then the 4 bounding boxes for the second box. All right, so that's the sort of the overview of the model architecture, but of course we need to implement this. All right, so I've just created a folder and right now it's empty. So sort of what we're gonna do is we're gonna create a model.py, and let's create the other files that we're gonna use later on. So we're gonna use loss.py, we're gonna implement that later on. We're gonna use train.py. We're gonna have a utils file with IOU and a no-max suppression and mean average precision. And then we're gonna have a dataset.py. So if we look now, those are the files that we're gonna have, and we want to first start with the model. So first thing, we're gonna import torch. We're gonna import torch.nn as nn, and I'm actually gonna copy paste something here. And this is going to be the architecture configuration. So this is sort of done by hand from the paper, and perhaps I can put it side by side so you can view it from how the model looks. So each tuple is structured by, first of all, the kernel size. So in the first it's 7, then it's the number of filters as output, and then it's the stride, and then it's the padding. So the padding, in this case 3, is also calculated by hand. All right, so that's for the first thing. So, all right, so this right here is going to be the first. Then we're going to have a max pool, which is just M. Then we're going to have a 192 output, and then 1 stride, one padding, and then a max pool again, and you get the point. So these are all conv layers representing the kernel size, the output filters, the stride, and the padding. So let's do tuple. Tuple is kernel size, num filters, stride, and padding. All right, so then we have this list right here. So the list is going to be, inside we have tuples. So let's see. So in the list we have one tuple. So, and this again also represents the kernel size, the num filters, the stride, and the padding. And then we have another one. And then the last value here is how many times those two tuples should be repeated in sequence. So we're going to have, that tuples, and then last integer represents number of repeats. All right, so then again we have a tuple, so a conv layer, max pool. Then we have another of these lists, and inside that we're going to have that those two conv layers are going to be repeated sequentially 2 times. And then we have again 4 conv layers at the end. And this is not including the fully connected layers to have the 7x7x30 output, but this is just the conv layer layers, so to speak. So we're going to go down a little bit. All right, so we're going to first create a class CNN block. So we're going to reuse this multiple times. First of all, we've got to inherit from the NN module. Then we have to create our init. So init. We're going to send in the in channels. We're going to send in the out channels. And then we're going to take some keyword arguments. Let's just set it to quargs. And we're going to first call super of CNN block self init to initialize the parent class. And then so the CNN block is going to be a conv layer, a batch norm, and then a relu. And so one thing here is that they used leaky relu instead of relu in the paper, but they did not use batch norm. That's actually something that wasn't invented at the time, but I really find no point in not implementing it. So I feel it's very easy to include. So we're going to do, first of all, nnconv2d. We're going to have number of in channels, number of out channels. We're going to set bias equals false because we're going to use a batch norm. So then we're going to use quargs. We're going to do self.batch norm equals nn batch norm 2d. And out channels is going to be the number of channels. And then self.leakyRelu is going to be nn.leakyRelu. And then they use 0.1 for the slope. And then for the forward, it's going to be very simple. We're going to do a return self.leakyRelu, self.batch norm, self.conv of x. All right. So that's just a CNN block that we're going to sort of use many times. So then we're going to do class YOLOv1. So this is, we're going to call it v1 because there are 4 different versions of YOLO. This is the original paper, so let's just call it YOLOv1. Then we're going to have an module. We're going to have an init, self, in channels. We're going to set in channels to default by 3, equal 3. So we're using RGB images. And then we're going to have some keyword arguments sent in as well. So we're going to first call super YOLOv1 self init. And we're going to do self.architecture equals architecture config, which we did in the beginning of the file. We're going to have self.inChannels equals inChannels. Then what they sort of call the conv layers is darknet. So they call that darknet, and that's actually a framework that Joseph Redman has done, has created as well. But so that's the conv layer part, and then the fully connected is just the top of that, what he calls darknet. So we're gonna do self.darknet, and to create that, we're gonna do self.create conv layers, and we send in self.architecture. So we're gonna implement this, but this is gonna be built from the architecture. So that thing is called darknet. Then we're gonna do self.fully connected at the end, we're going to do self.create fully connected, and here we're going to send in some keyword arguments. Okay, so now what we're going to do is we're going to do a define forward self of x, and we're going to return self.fully connected of torch.flatten, or rather x equals self.darknet of x. Then we're going to do self.fully connected torch flatten of x, and start dim equals 1 because we don't want to flatten the number of examples. But so we're going to flatten it, and we're going to send it to fully connected. And all right, so now we actually have to, do the hard part. Now we've only done the easy part, so we got to create the darknet. So define create conv layers. We're going to have self, and we're going to have some architecture. We're going to have layers be an empty list. So we're going to put everything in this list. And then the in channels is going to be self.inChannels 3. And then we're going to have for x in architecture. We're going to check if the type is a tuple, then that means that we're going to add a CNN block. And we're going to add it with in channels. Let's see if I can put this. And we're going to have in channels. Then we're going to have the kernel size. Let's see what we call that actually. So in CNN block, we called it out channels. Yeah. So the out channels, let's see, the out channels is going to be x of 1. That's how we structured the tuple. Then we're going to have kernel size equals x of 0, stride equals x of 2, and then padding equals x of 3. So let's see if we can clean this up a little bit. So let's remove actually the out channels here. Let's just put x of 1 like that. Then we're gonna close that CNN block, and we're gonna close. Yeah, so we also gotta do that. This is a tuple, like that. So all right, so like that. So we're gonna, layers. We're gonna add, if it is a tuple, we're gonna add a CNN block with in channels. Out channels is x of 1, kernel size is x of 0, stride is x of 2, and padding is x of 3. And that's all in the configuration of that tuple. Else, if the type is if type of x is a string, then we're gonna add we're gonna add a NNMax pool 2D with a kernel size of 2 by 2 and a stride of 2 by 2. And I guess we can also clean that up a little bit, and we just have to write 2 because it's going to be automatically expanded to 2 by 2. Then let's see, did I close everything here? No. All right. So then else if the type is a list, right? So this might be also be the tricky part. So if it's a list, then we're going to take the conv1 is x of 0, conv2 is x of 1, and then the num repeats is going to be x of 2. So remember, every list just had two conv layers that were repeated sequentially. So conv1 is going to be x of 0, and so this is going to be a tuple, right? This is a tuple, this is a tuple, and this is an integer. So we're first going to do for underscore in range of num repeats. So we're going to do this a number of times. And we're going to do layers plus equals a list. We're going to call it a CNN block. And we're going to do that. We're going to have in channels. And the out channel is going to be conv1 of 1, right? That's the tuple, similarly as we did up here for x1. But now we're going to have conv layer 1. Then we're going to have kernel size. It's going to be conv1 of 0. The stride is going to be conv1 of 2. Padding is going to be conv1 of 3. And then we're going to close that CNN block, and we're going to close that list. All right, so that's for the first one, right? Then we're going to have layers plus equals CNN block. Then we're going to have conv1, 1, conv2, 1, and because remember the in channels now is actually going to be the output from the first conv layer. So we need to have that the in channels is conv1 of 1, then the out channels is going to be conv2 of 1, and the kernel size is going to be conv2 of 0, stride is going to be conv2 of 2, padding is conv2 of 3. We're going to close that, close the list, and then we got to sort of change that the number of in channels is now going to be the conv2 of 1. So the output channels of the second conv layer is going to be the input to the next time we run this loop. All right, so that was a lot of stuff. Let's see if we can find where we should now return things. So return nn.sequential, and we're going to do this star layer. So that's going to unpack this list and convert it to an nn sequential. All right, so hopefully, let's see if this seems correct. That's where we should do the return. All right, so so that's for the darknet, and this can feel a little bit tricky, I guess, but remember that everything is in the configuration file, so we're just trying to use that in a clever way so that we can have compact code. So it might take some time to just read through it and make sure that you understand it. All right, so then for the create fully connected layers, we're gonna have self. We're gonna have the split size, right? That's S. Maybe I should just call it S. So S. We're gonna have num boxes, and then we're gonna have num classes. So we're gonna have S, B, C is gonna be the split size, the num boxes, and then num classes. Yeah, so let's call it split size. Split size. All right, so then we're gonna return nn.sequential. First of all, nn flatten. So we're gonna want to flatten everything because we're gonna send it through a linear layer. Then we're gonna do nn.linear. It's gonna be 1024 times s times s, and then output. So in the original paper, this is 4096 here, but so it's gonna take a long time it's gonna take up a lot of VRAM with those many nodes. So I'm going to put it to 496, but just note that this is in the original paper. This is for this 4096. Yeah. So then we're going to do nn dropout, and let's set it to just 0 by default, but it should be 0.5. Then we're going to do nn leaky relu, or an 0.1 as a slope, and then nn.linear 496, and then we're going to output s times c plus b times 5. So here, we're outputting s by s times the number of classes plus the bounding boxes times 5, because these bounding boxes have a probability score and 4 bounding boxes associated with it. One thing here is that we're going to have to do a reshape later on. I think that we do that in the loss function, but this is just a linear layer, of course. Yeah, so this is then going to be reshaped to be s, 30. So c plus b times 5 equals 30. All right, so that's the model architecture. So we've implemented that. Maybe we should do some kind of test case. So let's do that. Let's do define test. And let's send in some split size equals 7, num boxes equals 2, num classes equals 20, and then let's do model equals YOLOv1 of that split size, and then the num boxes, and then the num classes. And let's also do x is torch.random of, let's just do 2 examples, 2 and then 448, 3. And then let's do print model x.shape. All right, so yeah, we specify that this should be a keyword argument. So let's just do that this is equal b, and this is s, and this is c. So we're going to send in here that the split size equals s, the num boxes equals b, and num classes equals c. So let's try to rerun that again. Okay, so unsupported operand type S for tuple and integer. Oh, yeah, so I made a mistake here. Self.inChannels should just be equals in channels, not with this comma right there. So let's remove those prints. Is it just me that only debugs using print statements? Anyways, so let's run the model, and there's an error again. Torch.nn has no attribute leaky rel. Yeah, so rel. I think this should be capitalized. Rel. What the hell? Like that. Oh yeah, sorry. So this is 448. This should be 3. 448. 448. Yeah, like that. Yeah, so one thing here, it's also incorrect right there. It should be that, of course, when we've done the CNN block, the in channels to the next com layer we're going to create has to be modified. So the in channels now is going to be x of 1 instead of keeping equal in channels to 3. So you remember we did that update below here when we had the list. Then we did the in channels equals com2 of 1. But we need to also do it for the right here for the CNN block. Hopefully that is it. Please, please. Yes. So if we would take this 1470, we can reshape that. So, you know, if we would do, let's see, S7 by 7 by 30, that's 1470. All right, so that at least works as a sanity check. So, so that's our implementation of the YOLO model architecture. That I'm not sure how long that took. So here is the loss function for the YOLO algorithm, and there's a lot here. All right, so we have to step through it part by part and try to make sure that we understand this, and hopefully it will be even clearer when we actually get to implementing this. So first of all, let's just look at the sort of the overview of all of these losses. So all of these these parts of the loss function are going to be some squared error. So we're going to take the error squared and then take the sum. And, you know, more specifically, if we look at this one up here, then we're going to have, this is for the box coordinate for the midpoint. All right, so we're taking the midpoint x value, subtracting it with the predicted, taking that squared, plus the y value minus the y predicted, taking that squared. Okay, then this part right here is an identity function, and essentially we're only going to do that, first of all, if there's an object in the cell, and also if the bounding box j is responsible for outputting that bounding box. Okay, so I'll say that again. This is an identity function, this I right here, and the identity function means that it's going to be 1 or 0, and it's going to be 1 if there's a box in cell I, all right, and I is going to go from 0 to s squared. So I is going to go from 0 to s squared, so it's going to go through every cell in our image, and so it's going to be 1 if there's an object in cell I. But additionally, we need a requirement that bounding box j was responsible for outputting that bounding box. All right, so you might ask, well, how do we know which bounding box is responsible for outputting that bounding box? And if we just scroll down in the paper, let's see, it says here, it also penalizes bounding box coordinate error if that predictor is responsible for that ground truth box, i.e. it has the highest IOU of any predictor in that grid cell. So what this means is that we're going to look at a cell and we're going to see which of our bounding boxes, our predicted bounding boxes, which we have 2 of, has the highest IOU with the target bounding box. The one that has highest IOU, right, highest IOU, is going to be the one responsible, and that's the one we're going to send in right here. So we're only training the one here that's actually that was the best prediction. So because otherwise this is going to be 0. All right, so we do that, and we go through every cell and see if there is a object in the cell or not, and then we sum all of those together. Then we multiply with this lambda chord, and this is just going to be a constant because we want to prioritize this a little bit higher. So we're going to multiply all this loss by 5 because we really want to make sure that we can get the bounding boxes correctly. All right, so the second is right here is for the width. So we do the same thing pretty much. We have the identity function, we have the width minus the width prediction squared. The only difference here is that we have the square root. Let's say that we have a very large bounding box and we take those subtract and we take it squared. For very large bounding boxes, that squared is going to become very large. But for small bounding boxes, the loss is not going to be as large if you would have a larger bounding box. So what they do is that they take the square root to make sure that we prioritize smaller bounding boxes equally much as we do for large bounding boxes. And then we still have the identity right here, and we have the sum, and then we have lambda chord right there. All right, so those two on the top right there are for the coordinates, all right, for the box. All right, then for the next one right here, we have that C in this case stands for the probability that there's a box. So that's what we looked at previously. That was PC, the probability that there's a box in the cell. And so again, here we're only going to take the one that has the highest IOU, and that's the one that's going to be sort of responsible for predicting that there's an object in this one. So CI is going to be 1, and we're going to want to predict that the probability that there's an object is going to want to be close to 1. And so we go through for each cell and we go through every bounding box. Next is if there would be no object in a cell. Then we have this loss right here. So this, first of all, this loss above is if there is an object in the cell. The thing below here is if there was not an object in the cell. And then we're going to have that this identity no object, ij. So we're going to look if there's no object in cell I. And here is actually one thing that I found pretty difficult interpreting. So if there is no object, which is the one responsible for outputting that there's no object? In this case, they say that the one responsible is the one with the highest IOU. But in this case, they do not, or it's not clear to me which is responsible. Perhaps you can view it that it's the one with the lowest probability. That's the one responsible, or rather the highest probability. So you take the worst out of the two, and that's the one responsible. But in my opinion, it makes more sense to, if there's no object, then we should train both of the bounding boxes to make sure that both of them say there's no object here. So that's my interpretation of this, at least. And then we take the lambda no object, which is going to be 0.5, if I remember correctly. It's just going to be a constant to make so that we don't want to prioritize this as much. All right. So then for the last thing right here is for the classes, to make sure that we actually can say what object is it in this box, or in this cell rather. What we do is that for each cell we look, is there an object here? So the identity, if there's an object in cell I. Then we go through each class, all of the 20 different, and again we take the sum squared error. And so normally here you would do something like cross entropy loss, use negative log likelihood and do it like that. But here they actually want to use a regression based loss for everything, which simplifies a little bit, and it works apparently. So that's what they do in this one. All right, so let's try now to take this sort of overview, this understanding of the loss function, and try to implement it in PyTorch. All right, so we're gonna first do vim loss.py. So we're gonna open up that file, and we're gonna need import torch, import torch.nn as nn, and we're also gonna do from utils import intersection over union. We haven't implemented, or we have implemented this, but I haven't put it in the utils file. So YOLO loss and then module. We're gonna define init self. We're going to specify the split size S and B for the number of boxes. So we have 7 by 7 grid. The number of boxes we output for each cell is going to be 2. And then we have 20 classes. So first of all, we got to do super on YOLO loss, self.init. And then we're going to specify our loss function. So self mean squared error. We're going to do mean squared error. We're also going to do reduction equals sum because they don't actually average it. So yeah, just trying to follow the paper right there. Then we're going to do self.s equals s, self.b equals b, self.c equals c. We're going to specify self.lambda no object is 0.5, self.lambda chord is going to be 5. So those are just the ones we need for the init. Then we're going to do define forward, and we're going to send in some predictions. We're going to send in some target. And remember that when we send it through the model, we need to make sure that they are reshaped so that they are s by 30. So we're going to do predictions equals predictions dot reshape. Let's just keep the number of examples. We don't want to reshape that. But we want to do self.s, and then self.c plus self.b times 5. So that's how we want to structure it. And then we're going to do, first of all, we're going to calculate the IOU for bounding for the first one. So we're going to do intersection over union predictions. And then we're going to take 21 to 25. Remember that we start at index 0, so 0 to 19, including 19 is going to be for class probabilities, 20 is going to be for the class score, and then 21 to 25 is going to be the 4 bounding box values for the first box. Then we're going to close that. We're going to take target. We're going to 25. Then we're going to do, let's see if I can copy this. We're going to do the same thing, but bounding box 2. And instead of taking now 21 to 25, remember, this is not including the 25th one. So we're taking 21, 22, 23, 24. But now we need to change this to 26 and 30. And still, though, there's only one target. So we're still going to have target 21 to 25. Then we're going to do IOUs are just torch.catenate of IOU B1. And we're going to unsqueeze just to be able to concatenate them. IOU B2 unsqueeze on 0. Then we're going to do dimension 0. So we're going to concatenate them along the dimension 0 that we just unsqueezed. All right, then we're going to take IOU maxes and the best box. We're going to take torch.max of IOUs along the dimension 0. So what we're doing here, torch.max is going to first return this thing right here, which we're not really going to use, but it returns the max values of the IOUs. But this thing right here is going to return the argmax of those, and that is something we want to use. So we're going to take which of the IOUs was the best one, meaning which one was responsible for that. Which one was responsible for that cell, or is responsible for that cell. Then we're going to do exists box is going to be target of 20. So that is going to be 0 or 1, depending on if there's an object in that cell. We're going to do unsqueeze 3. And yeah, so we could do 20 to 21 like this, but we want to keep the number of dimensions. When we take the 20th index, that last dimension disappears. So that's why we're doing unsqueeze here. We're gonna utilize this when we actually check for the loss functions. So this is, so you know, in the paper, this is the identity. So this is identity of object I. So yeah, identity. Maybe we should just write I object I. So this is going to tell us, is there an object in cell I? All right, so now let's do for, first of all, let's do for, so let me just copy in what we're gonna do. So first of all, so this is what we want to do. we want to first do for the box coordinates, and this means the midpoints and then the width and the height. Remember, we take the square root of the width and the height. Then we want to check what is the loss for the object loss, meaning if there is an object, we want to make sure that we output that, the probability of 1, there's an object here. If there's no object, we want to obviously say that there's no object. And then lastly, we want to make sure that it says which class the object belongs to. So those are the parts. So first of all, we want to take the box predictions. So the box predictions are going to be, first of all, if there exists a box, right, that we want to multiply. This is the identity part. Then we want to check which is the best box, and we want to times that with the predictions. So remember, this is going to be 1 if the second bounding box was the best. And the second bounding box is the one 26 to 30. But on the other hand, if the other one was best, so we're going to do 1 minus best box and times that with the predictions of 21 to 25. Because remember, this is going to be 0 if the first bounding box was correct. So best box is 0 or 1, depending on which one was best. And then we also times that with the existence of a box. So we only want to compute the loss if there is actually an object in that cell. All right. So after the box predictions, we're going to do the box targets, and that's going to be exist box times target of 21 to 25. Okay. So now we've taken for all 4, right? But what we want to do also is we want to take the square root of the ones that are for the width and the height. So we're going to do box predictions of all of them from 2 to 4. We're going to first do square root of the box predictions like that. But one thing here is that, if these box predictions are negative, which they are going to be in the beginning, just by initialization, then we have to take the absolute value, because otherwise we're going to get an error. So we have to do torch.square root, and we got to do torch.absolute value of the box predictions. But one additional thing is, what if there is 0, then the derivative of square root as you go to 0 is going to be negative infinity, or maybe infinity. Yeah, infinity. And so we're going to add, just for numerical stability, we're going to add 1e minus 6. And that's it. But we need to do one more thing, which is that when we take the absolute value, we need to make sure that the sign of the gradient is correct. So we're going to do torch.sign in the beginning here. So torch.sign of box predictions of all 2 to 4. We're going to take the sign of those, and we're going to multiply with the square root of the width and the height. Okay, so those are for the box predictions, and then the box targets, we're going to take 2 to 4, and these aren't going to be negative because these are just the labels. So we can just do torch.square root of the box targets of 2 to 4. And I guess maybe one thing I should be a little bit clear on is why are we doing this ... And remember that all of them are going to be, I guess, n, comma, s, comma, s, comma, in this case, 25. So we want to make sure that we do this for all of these dimensions. So we have an example, but we also have s by s cells. And that's why I'm doing ... Yeah, so that was just one thing. All right, so box loss is then going to be the self mean squared error of torch.flatten of box predictions, and we're going to do n dimension equals -2. So what I'm thinking here is that we want to, why I did n dimension equals -2 is because we want to flatten everything in front. So, you can kind of view it that these n, s, s by 25, all of these are sort of separate examples in a way. So what we do is that we send in n times s by 25, or rather, sorry, 4 for the bounding boxes. So this is not going to be 24. This is going to be 4, like that. And so this is going to become n times s by 4, because that's how a mean squared error expects the input shape to be. So that's what I believe, why I did that. And we're going to do torch.flatten of the box targets. And again, n dimension is going to be equal to -2. So we're going to close that. Then that's the mean squared error of the box loss. Yeah, so then we're going to do the object loss. So for the object loss, we're going to do, first of all, which was the prediction. And we're going to do that by taking the best box. That's the one with the highest IOU. I'm going to take that time to predictions of 25 to 26. And so we're taking out the probability score. And why I'm doing this slicing right here is just to make sure that we keep the number of dimensions. So yeah, that's the only reason. And then we're going to do 1 minus best box, because if the best box is 0, then this is going to be the one that sort of takes over and is responsible. So then we're going to do predictions 20 to 21. And we're going to close that. And then we're going to do object loss is equal to self.mean squared error of torch.flatten of exists box times pred box. And why we're doing this is because we want to flatten to make sure that we have the same shape that mean squared error is going to take as input, which is that we have the number of examples here, or in this case n times s, comma 1. So we're gonna take that for all of these cells for each example. And I think we don't have to specify the start dimension here because it's going to do that by default. All right, so then we're going to do the same thing, torch.flatten of exists box times target. Like that. No, like that. So that's the object loss. And so, we're first checking which one of those two are responsible, which of the bounding box predictions are responsible or is responsible. And then we're checking if there actually exists a box. So this is for the identity part of the loss. So that's for if there is an object. In the case where there is no object, my interpretation here is that we're going to take the loss for both. Because if there's no object, I'm thinking it only makes sense that both of them should know that there's no object. So we're going to do no object loss equals self.mean squared error of torch.flatten of 1 minus exists box times the predictions of 20 to 21. And we're going to take start dim equals 1. I'm not really sure if we need to do that. Oh, maybe, okay, so maybe here, this torch.flatten, I should probably check this up again, but I think torch.flatten here might flatten the entire thing. So, and that makes sense. We don't have to have this comma 1, so we can just have that. But here we want to specify start dim equals 1. All right, so I think I'm starting to notice that there's a little bit of an inconsistency in how I've done this torch.flatten. In this case, it seems that we're flattening so that we have n, comma s, comma, in this case, just 1 for the no object loss, or no object for the box probability. This is going to be n, comma s times s, which I guess also works. But yeah, so I guess you could also modify this. I don't dare to do it though, because I want to make sure that the thing I've done that works is the one I'm implementing. But I'm thinking that you could also flatten this in some different ways. But yeah, so as long as we understand what's going on here, I think it's good. So then we're going to do torch.flatten. We're going to do 1 minus exists box. I'm going to times that with the target of 20 to 21. And again, we're going to specify start dim equals 1. And that's it for the first one, right? But then we got to do no object loss. And then let's do plus equals self.mean squared error of yeah, so let's actually just copy this because it's going to be very similar. So I'm going to take that and I'm going to remove that part. and then we got to do plus equals, and it's going to be 25 to 26, and then the target is still going to be 20 to 21. All right, so we're doing this now for both of them, which is how my interpretation is that we should do. All right, so for the class loss, we're just going to do class loss equals self.mean squared error of torch.flatten of exist box times predictions up to 20, right? So we're taking all of the 21st nodes, and the n dimension here is going to be -2. And so what we're doing here when we're taking n -2 is that we have n comma s comma s comma 20, and we're making this into n times s comma 20. So we're kind of viewing that each cell is a separate example, which I guess makes sense as well. And then we're going to do torch.flatten. We're going to do torch.flatten of exist box times target of up to 20, and n dimension is going to be -2 as well. And then we close that right there. And now for the actual loss, we have all those losses. So we're going to do loss equals self.lambda coordinate times box loss. So this is going to be first 2 rows of paper of I guess loss in paper, and then we're gonna add object loss here. Then we're gonna add self.lambda no object times no object loss, and then we're gonna add the class loss. So this would be the 3rd row, this would be the 4th row, and this would be the 5th row in the paper. All right, and then at the end, we're just going to return loss. So what I'm going to try to check here is I'm going to put this in the complete directory and make sure that this works, because I haven't done test cases for this separately. All right, so let's just see. Here is the sort of complete folder. So I'm just going to see Python train. Yeah, we got a conda activate deep learning. All right, best box is not defined. Best box, okay, I used best underscore box. So let's run that again. Best box is not defined. What? We just did that one. Yeah, this should be best underscore box. So let's put this again and see if it works. Oh my God, best box is not defined. Where did I put that? Line 29 here, but it should, right? Oh, yeah, so, of course, I'm not modifying that file. And so I need to modify that file. Let's see, so, okay, so now we can check. Hopefully it works now. Nope, line 53, best box, and then best box. Yeah, all right, all right, and it seems to work, nice. All right, so that was the complete sort of code that I ran it on, just to make sure that it works. And so now we have a correct loss function implementation, hopefully. All right, so now we have done the model.py and we've done the loss.py. But maybe before we do the training, let's actually make sure that we have the data set set up. So before we actually implement the dataset class for loading the data, we need to make sure that we have the data, which involves quite a lot of steps, to be honest. So what I've done is that I've uploaded a zip file on Kaggle, that there's a link in the description. You can go there, you can download it. And this is actually going to be so this is 4 gigabytes, but I'm going to upload a smaller version if you don't want to download that entire thing, maybe few hundred megabytes or 100 megabytes or so, with just a couple examples so you can play around with the code. But if you want the entire data set, that's here, and then all you have to do is extract here, and then we should get a folder right here containing the data, and that's that's everything we're gonna need. So let me just wait until this is finished. So if we open up that data folder, we're going to have, first of all, I guess the thing that's important is we're going to have a train.csv file, we're going to have a test.csv file, and we're going to have labels and images. So inside this, there's going to be, I don't want to open it because it's going to take a long time. Whatever, let's open it. All right, so there we go. We get a ton of images. All right, I think it's, I don't know how many, 25,000 maybe, 30,000. So we get all of those. And if we go back, if this will load, I already regret doing this. So then we have the labels, and I'm not going to open that, but those are just text files. Okay, I'm going to open it. So there we go, just text files. And if we open up this, for example, what we'll see is this right here. So we'll see, first of all, which class this belongs to. Then we'll see the center location, and then we'll see the, wow, this is so annoying. So the first thing we're going to see is the class probability. Then we'll see the midpoint. Then we'll see the Y midpoint. Then we'll see the width and the height. Now, one thing here is that these are not relative to a cell, right? We can't know, that depends on how we've split it. These are relative to the entire image. And so what's great is that if you resize it, to different number of pixels, then this is still going to work since it's relative to the entire image. So one thing that I think a lot of you are starting to realize is that, well, we're going to have to do this conversion of having from the entire image to having just the ratios for each cell. So that's one thing we're going to do in our dataset class. But anyways, that's how the data is structured. So in this case, this image would have two bounding boxes, two different objects of class 11 and class 14. All right, so that was kind of for making it easy. If you just want to download from Kaggle and you'll be done, so to speak, you don't have to do anything. If you want to do it by not downloading from Kaggle, or you want to see what it does step by step, then you can read this bash script. But what it's going to do is if we run that, so let's see, yeah, if we run that, then it's going to, first of all, download those data sets. It's going to it's going to sort of unzip them or untar them, I guess is the correct. But it's going to do that, and it's going to do a lot of pre-processing, and it's going to generate the CSV file and all of that stuff. But I don't want to focus too much on that. If you really want to read more about it, then you can read through this generate CSV file and go through the bash script of what's actually going on. But I'm assuming that for the majority of you, that's not interesting. And so just download this zip file from Kaggle and unzip it, and you'll have everything you need. All right, so now we gotta implement this stuff, right? All right, so now that we have the data in a data folder, we're gonna do vim dataset, open up the dataset Python file, and we're gonna import torch, we're gonna import os, import pandas as pd, and from pill import image. So those are the packages we're gonna need. And we're going to first do class VOC dataset, and we're going to do torch utils.data.dataset. We're going to inherit from that. Then we're going to do define init, and we're going to do self. We're going to send in a CSV file for the locations of, for the CSV file that contains the image and also the label. So let me actually be a little bit clearer on the data. So, we took a look at the images and the labels, but one important thing is that we actually need to understand the CSV file. So if we open up, let's say this train.csv, then we'll have the image, in this case, 5.jpg, and then 000, same number of zeros, 5.txt. So we have the image and we have the text file. And so they're located in this folder right here for images and then in labels. But of course, everything is sort of in that CSV file. So we're going to have CSV file. We're going to need to know the image directory. We're going to need to know the label directory. Then we're going to need to know the split size, the number of bounding boxes, and then see the number of classes. Then if we have potential transformations we want to do, we're going to set that to default to none. And I'm not actually going to go through data augmentation for object detection in this video, but if that's something you would be interested in, let me know and I'll consider making a separate video. All right, so then we're going to do annotations. We're going to first read that CSV file. So we're going to pd.read CSV of that CSV file. We're going to do self.image directory to be image directory, label directory equals label directory, and then self.transform equals transform, and then self.s equals s, self.b equals b, self.c equals c. All right, so then we're going to do the length. So that's going to be return the length of self.annotations. And if you're confused of any of this so far, then make sure you watch my video on creating custom dataset loading. So we're going to do then get item, self, and then comma index. So what we got to do first of all here is that we're going to find the label path. So we're going to do the label path is ospath.join of the self.label directory, which is just the directory we saw in labels. And then self.annotations dot, we're going to locate an index row, and then we're going to take the first column because that's where the text file is. Then we're going to do boxes. It's just an empty list. And we're going to, with open label path as f. So now we're opening that text file. We're going to do for label in f.readlines. We're going to do class label, comma x, y, width, and height. So this is going to be equal to float x. And I'm going to write this out and I'm going to explain this in a little bit more detail. If float x is not equal to int of float x, else integer of x. And we're going to do that for x in label.replace. We're going to replace a new line with just empty space, and then we're going to do dot split. So all right, so what am I doing here? Remember that the class is going to be an integer, and we want that to be an integer, but the rest of them, x, y, width, and height, are very likely going to be floats. So what we're doing is that we want to take the float if the float is not equal to the integer of that float. So remember, it's a string, so when we're doing float, we're converting it to a string, and then we're taking the integer part of that. So if they're not equal, then it means that it's a float, right? So we're going to take the float of x, converting that string into a value. Otherwise, we want to take the integer. If they are in fact equal, then that means that it's just an integer, and we want to do integer of x. All right, so then we have the class label x, y, width, and height. And what we're going to do is boxes.append. We're going to append class label x, y, width, height. So, sort of in summary, all we're doing is we're reading that a particular line, we're converting it to floats and integers, and then we're appending it. All right, so then we're kind of done with the label part, and we're now interested in the image. So we're going to image path is ospath.join, self.image directory, and then self.annotations.locate, index, and then 0. So that 0. So we're sort of getting the image directory, and then we're getting the image file name, which is index, comma 0. Then we're going to do image equals image dot open of image path. We're using pill here. Then we're going to do boxes is going to be torch.tensor of boxes. So we're just converting it into a tensor. And actually, I'm not sure if we need to do that. So we're converting it to a tensor, and then we're doing if self.transform. If we have transforms, we're going to do image.boxes equals self.transform of image, comma boxes. And I guess why we want to send in both here is because if you're doing, let's say you want to rotate the image, then this is getting into data augmentation for object detection, which can be quite tricky. But in many cases, let's say you're doing a random horizontal flip, then you obviously want to change the boxes as well. We're not going to go into that in this video though, but that's how you would do it. Then we're going to do the label matrix. It's going to be torch.zeros of self S, self C plus 5 times self comma b, right? So it's just going to be s, and then 30, or rather, no, sorry, this should not be self.b here. Yeah, so sorry about that. This should be just plus 5 because we should only have one bounding box per cell. But now I'm kind of afraid that this is going to break something, but let's see. So then we're going to do for box in boxes. And what we kind of want to do here is we need to convert everything to fit this label matrix right here. Remember that this is now relative to the entire image. And we want to first see, well, which cell does this bounding box belong to? And then we need to convert it to be relative to that cell. So we're going to do class label xy with height equals box and then dot to list. So this looks kind of weird in a way. Why are we converting it to a tensor and then converting it back to a list? But I think the idea is here that if we're doing any transformations, you most likely are going to do them in PyTorch. So that's why we're doing it that way. And then here we gotta convert them back. But yeah, so there you could probably also change them in this. But anyways, we're converting it back to a list now. And let's just make sure that the class label is in fact an integer. So let's do integer of class label. All right, so now we want to convert to seeing which cell row and cell column should this belong to. And how we do that is we do I comma j to be the integer of self time comma s times y. That is the row that it's going to belong to. And then we do integer of self.s times x. And that's going to be the cell column. So, remember, this is going to be a ratio between 0 and 1. And we now want to convert it where every cell is 0 and 1. So to know which cell row and cell column it should belong to, we just need to scale it appropriately by multiplying with the number of cells that we have. And then we take it, sort of down by taking the integer of that. And then we do that the x relative to the cell and the y relative to the cell is going to be self.s times x minus j, and then self.s times y minus I. So then we're kind of doing this relative to the cell by removing in which part of the cell it's in. So yeah, maybe these two lines can be a little bit tricky, but I recommend that you take an example, draw it out, and then do this by hand and see that it works, if it's not clear instantly, so to speak. And then to get the width compared to the cell and the height compared to the cell, all we have to do is take the width times self.s and the height times self.s. So remember, this is going to be the width and the height relative to the entire image. And if we want it relative to one cell, all we have to do is scale it appropriately with the number of cells we split it by. So that's how we get the sort of all of these are getting the locations relative to the cell. All right, so what we got to do now is we got to do if label matrix of the cell ij is equal to, and then 20 is equal to 0. So we're checking if there's currently no object in ij, which we just calculated that this object, this bounding box should be in. Then first of all, we want to make sure that this is now taken. So this is going to be 1 in the future. And then we're going to do that the box coordinates are going to be towards the tensor of x cell, y cell, width of the cell, and then the height of the cell. And we're going to specify that the label matrix I comma j and then 21 to 25 is equal to these box coordinates. And also that the label matrix of I comma j comma class label is going to be equal to 1. And so here we're just specifying which should contain the class, or which class it is for this object. And that's it. So what we got to do now, we just got to return the image and the label matrix. And I guess one thing to remember, recognize here, is that this is just for one example, but that's all we have to do with loading custom data in PyTorch. We specify how to load one example, and then we're going to have some efficient data pipeline that's going to batch and everything and do everything of that stuff for us. All right, so that's for loading the data. I know it's a lot. This is a large project. And I'm just going to check that this is actually correct. So I'm going to run this on the complete code, see that it works. So we're going to do Python train.py and Python. So I've now copied in replacing the other data set, and that's not correct. So let's see, on line 24, right there, we've got to do label path. So let's bring that back. Okay, so after some troubleshooting, I found that another file that I am using is assuming that the shape of this should be 30 for the labels and predictions. So we're gonna have to do self.b, so it's 5 times self.b, and that makes so that I don't have to modify the other file. But just note here that the additional 5 nodes is not going to be used. The only things that's going to be used are the 25 first nodes. So we're not going to actually need 30. That's for the predictions because we have one additional bounding box. And so where I actually assume that this was 30 nodes is when later on reconverting this to being relative to the entire image. That's when another function sort of was, I guess, assuming that this should be 30. But anyways, we can just put it to 30. It doesn't really matter. But that's just one thing to keep in mind. So, wow, we've now done, let's see, we've done the model, we've done the loss function, we've done the data set, and what we're not gonna go through the utils, but what's going to be inside there is intersection over union, null-max suppression, mean average precision, where we've done all of those through in previous videos. One additional function I'm going to put in there is converting from relative to cell to being relative to the entire image. And I'm not going to show how to do that, but it's going to be on GitHub if you want to read it. I don't think that code is super interesting. And then what more? There's going to be one additional there as well, which is how we can plot these bounding boxes. And to save some time, I'm not going to go through that either. But that's also going to be in GitHub if you want to see. That's mostly for making sure that our model works. That's the only reason, basically. So what we're now going to do is the train function. So we're going to specify how the training should be done and all of that stuff. So let's open up vim train.py. And so we're going to import torch, import torch vision.transforms as transforms, import torch.optim as optim, import torch vision.transforms.functional as functional transforms, FT. We're going to import, and so these are for the transforms, the optimizer. This is also for some image transforms we're going to use. Then from TQDM, import TQDM. That's a video I did on how to get a progress bar in PyTorch, just so that it looks nice. So that's all we're going to use that for. Then from torch.utils.data, import data loader. We're going to do from model, import YOLOv1. From dataset, we're going to import VOC dataset. From utils, we're going to import intersection over union, non-max suppression, mean average precision, and all of those three are separate previous videos in this playlist. So if you're unsure about any of these three, check out those videos because that's code copy pasted from those. Some more that we're going to need, and I'm not going to show how to implement these, but it's going to be on GitHub. But it's going to be cell boxes to boxes. So converting from the cell relative to the cell, so we get them in relative to the entire image. Then we're also going to do get bounding boxes, and this function is going to use this one, converting it, and then also get all of the bounding boxes. Then we're going to do plot image and save checkpoint, load checkpoint. So I guess the only thing I'm not going to show, these two I've done previous videos on, and hopefully this should be pretty simple. But this right here, sell boxes to boxes, get boxes. So these three, I'm not going to show how to do. I don't think they're very interesting, but they're going to be on GitHub. Lastly, we got to do from loss import YOLO loss. We're going to first set a seed. Let's do 1, 2, 3. Torch.manual seed of seed. And this is mainly so that we get the same data set loading, but that's pretty much all. And then let's set hyperparameters and so on. Let's first start with the learning rate. So learning rate, let's set it to 2e-5. Device, we're going to set to CUDA if torch.cuda.is available. Otherwise, we're going to set it to the CPU. The batch size, we're going to set to 16. Because we have so large images and the model takes a lot, even if we've set the number of nodes to 496 instead of 4096, I can't have the batch size that they mentioned in the paper, which is 64. The maximum I can go is a batch size of 16. And so that might be saying that I need an upgrade in my GPU, but I'm using a GTX 1060, so I don't really have that much compute. But batch size equals 16 it works fine. So we're going to set weight decay equals 0. And so why we set the dropout to 0 and the weight decay to 0, why we're setting it here, is because I'm not actually going to train the entire model to re-implement the exact same results they got in the paper. And there are two reasons. First of all, that's going to take a long time to train. They pre-trained on ImageNet for 2 weeks, and then they trained on this data set for a long time. And they also did it with very heavy data augmentation. And frankly, even if they did it a couple of years ago, their GPU was a lot better than the one I have. So it's mainly because of computational reasons. And so what we're gonna do to make sure that this actually works is we're gonna first try to overfit a single batch. We're gonna plot and see that it makes sense, and also see that we get a mean average precision of close to 1. And then additionally, we're gonna overfit 100 examples. So those two are sort of sanity checks to make sure that our implementation is accurate. But to do that, to overfit more easily or faster, we're gonna set so that we have no regularization. All right, so we're gonna set epochs to, I don't know, 1,000, 100 maybe. And then we're gonna set non-workers to 2. And this is a hyperparameter, so you play around with that. We're gonna set pin memory to true. Load model to false. Then we're gonna set load model file to be, we're gonna call it overfit.pth.tar. So this is just so that we save the model that we overfitted, and we're gonna run it later on to see that when we plot images and so on. So the image directory, first of all, then is gonna be data images. The label directory is gonna be data labels. All right. So, one thing we got to do is we got to make sure that they are resized. So I'm actually going to create, so we can use transform.compose, but that's not also going to take in the bounding boxes. And now when I think about it, when we're just doing resize, this is going to look a little bit odd perhaps. And you could just have done transforms.resize. And then when sending it in, you could just have only sent in the image because we're not doing any data augmentation on the label side. But in my implementation, I checked for doing some data augmentation like horizontal flip and random crops and so on. And what I'm doing here is going to extend more easily if you have more data augmentation. So we're going to do our own compose. And we're going to do our init self comma transforms. We're going to do self.transforms equals transforms. Then we're going to, when we call this, we're going to send in the image and bounding boxes. We're going to go through for t in self.transforms. We're going to do image bounding boxes equals transform of image and then bounding boxes. And the reason here is because our transform that we're going to send in is only going to operate on the image. But of course, if you would modify them, then you would have that you would also do them on, you would then send in, if you would create your own, you would do like this. But so in this case, we're only going to do it on the image because we're only going to resize it. So do transform equals compose of transforms.resize, and we're going to resize it to 448. Then we're going to do transforms.toTensor, and we're going to close that list, and that's the compose. So we're going to resize and then transforms to tensor. One thing that could improve this is that you do a normalization, so you make sure you have mean 0 and standard deviation 1. But to tensor, I guess works fine in this case. All right, so then we're gonna define a training function. We're gonna send in a training loader, the model, optimizer, and the loss function. So what's gonna be done here is one training loop through the entire data set. First of all, we're going to do loop is tqdm of train loader. We're going to do leave equals true. This is from the video I did on setting up a progress bar. But then we're going to have mean loss is an empty list. We're going to go through for batch index, comma x, comma y in enumerate of this loop. We're going to do xy equals x dot to device, and then y.to device, and the out is going to be the model of x, and we're going to do loss is loss function of out and then y. We're going to do mean loss dot append loss dot item. So obviously here we haven't actually created these things. We haven't created the loss function and so on, but this is going to be done later on. So we're going to do optimizer.0grad. We're going to do loss.backward, optimizer.step. And then let's see, right here we gotta update the progress bar. So how we do that is we do loop.set postfix, and I'm just going to send in the loss. I'm just going to do loss equals loss.item. So for the progress bar, we're going to see that the loss updates for every batch. That's just a nice thing to have. And then we're going to print the mean loss was, and then sum of mean loss divided by the length of mean loss. So we get the mean right there. So that function is just going through the entire train loader once. So we trained on an entire data set. Let's put this centered. So what we got to do now is we're in main, and we got to initialize our model. That's going to be YOLOv1. We got to send in the split size 7, num box is 2, num class is 20, and then dot to device. We're going to specify the optimizer. It's going to be optim.atom. We're going to send the model parameters. Learning rate is going to be the learning rate. Weight decay is just going to be equal to weight decay. And that's it for the optimizer. The loss function is going to be YOLO loss. And here we're going to do, so if load model, let's make sure that I did that. So load model is false in the beginning. So if we load the model, then we want to do load checkpoint torch.load of load model file, model, and then optimizer also. So that's just if we have a model saved. And then we want to create a data set for training. So we're going to train data set is VOC data set of data, and we're going to specify the CSV file here. So that would be train.csv if you want to train on the entire data set. I'm not going to do that. I'm just going to do 8 examples.csv. So that's I guess, a small batch of 8 examples. We're going to try to overfit on that first, make sure that works. And then I have another CSV file with 100 examples. So that's what we're going to do. 8 examples. We're going to do transform equals transform, image directory equals image directory, label directory is label directory. And that's it for the training. So let's copy paste that. I'm going kind of quickly, but that is because this is very easy compared to what we've done so far. So I'm thinking this we're just calling those functions essentially. So let's see, we got to have the this should actually just be 1. So we're going to have the test data set here, and we're going to call it on, I guess if you would have, we would do test.csv, and that's it. Guess you can also write this on one line. So like this. I think that looks a little bit cleaner actually. But anyways, let's keep it like that. So then after that, we're going to do the train loader. That's just going to be the data loader. We're going to specify the data set to be train data set. The batch size is going to be equal to batch size. Num workers is just going to be num workers. Pin memory is to be equal to pin memory. So we've initialized all of them sort of in the hyperparameters list. We're going to do shuffle equals true. And we're also going to add one more. So drop last equals true. This is the case that if we have a batch and there's only 2 examples in that batch, then we don't want to do a gradient update step on that. I found that that could sometimes ruin the gradients if we do an update on only just a single example or 2 examples. So we're just going to, I don't think it makes too much of a difference, but we're going to drop last. And then test loader is, we're going to copy this. Test loader is test data set, and everything else should be the same. All right, so now we're going to do, let's see. We're going to do, first of all, for epoch in range of epochs, we're going to do call the train function. So we're going to train function of train loader, model, optimizer, and loss function. Additionally, one thing I want to do here is actually, I want to do the compute the MAP. So we're going to do pred boxes and then target boxes. It's going to be equal to get bounty boxes. And again, I haven't covered how to do that one, but all it's getting is it's getting us the get bounding boxes. And then we're doing the train loader, model, IOU threshold equals 0.5, threshold equals 0.4. So that is also calling null max suppression inside. So we're going through all of the examples, we're putting into pred boxes, getting the target boxes, and all of those are then going to be used for the mean average precision. So if you've seen that video, I think this should be relatively clear. So we're going to then calculate the mean average precision is mean average precision. We're going to send in the pred boxes, the target boxes, the IOU threshold should be 0.5 also, and then the box format for the IOU. So that's going to be midpoint. And that's it for that. Then we're going to do print the train MAP. We're going to do mean average precision and close that. So we're going to print the mean average precision in the beginning and then for every epoch. All right, that was a lot. So then we're going to do if name equals main. If that is the case, we're going to run main. So let's see, we're going to do Python train.py, and it didn't. All right, so line 45, this right there is going to be removed. Let's try running again. Division by 0. All right, so there were some mistakes in the code and I had to debug. So first of all, in the compose here, in the end, we need to return the image in the boxes. So that's one thing. Then also, since we set let me just clean this up. So remove those. One thing we did also, or I did, is that I set the drop last to true, which should not be the case if, for this case, we just have 8 examples. So it's always going to drop it since we have a batch size of 16. So we want to set this to false instead of true, just for this example, because we're trying to just overfit a single batch. Then over here, we can actually put this back as it was. So we can put it like that. I guess this doesn't matter too much. And then let's just make sure that we don't have a sysexit anywhere. All right, so let's now try and run this, and hopefully this works now. All right, so there we get an MAP of about 1, very close to 1. And so that makes us confident that it can overfit a batch. So let's see that we can, actually what we should do is we could check, we could do it like this. If the mean average precision is greater than 0.9, let's say, then let's do a checkpoint is, and I'm going to copy paste those in. So then we're going to do this. All right. And so this right there, we're going to do a checkpoint, and we're going to save the checkpoint. Then we're just going to do time and time.sleep, just so I have time to cancel it before it's saving again, because that would corrupt the file. So if that's the case, then we want to save it. Then we want to set so let's do that first of all. Let's run it and then train it, and then. So there's saving the checkpoints. I'm going to cancel it right there. And what we're going to do then is I'm going to copy paste some other code right there. And this code, let's see it like that. This code is going to go through the train loader. It's going to go through in range of 8. And we're going to plot the image for all of those so that we can see that it makes sense. So load model right there, we're going to set to true now. So we want to load the model, and let's run it. So that's our prediction for the cat. Those are our predictions for 2 cats. That's a prediction for the bike. And yeah, so you can probably improve this plot image. You can make it so that, I guess, each class has a different color, and then you can make it so that it has a title, and you can get that this is a bike. But yeah, sort of all we're doing here, and I've compared these to the target. This is how the target looks like as well. So for example, there's not a bounding box for this this woman, and then right there we have a car, and we have another car, and yeah, we have one for the guy on the bike, and we have one for the bike, and then another for this guy. So as we can see, this kind of makes sense visually. So what we can do now is we can try it on a little bit of a hard task. We can try it on 100 example. Make sure that it can overfit that as well. And let's put this drop last to true. And let's also uncomment or comment all of these things. Those are just for our sort of visual. We can save the model still, but that other part's just for visualizing. So let's run it again. All right, so after quite a while, we get training MAP of greater than 0.9. So if we just sort of look at the loss, we can see that it's 59, 57, and then it jumps up to 61. So the loss is jumping a little bit. We can see that there's a trend down, but it's not, a clear trend down. It's kind of jumping a little bit, 42, 49, 40. And also, there's not the MAP and the loss is not perfectly correlated. There's definitely a correlation, but sometimes the loss can go down, but the MAP doesn't improve. One thing I think you probably should do here is in the beginning we see that it's improving quite a bit, and then after some point it starts to jump a little bit, and I think using a learning rate scheduler here would be beneficial. But anyways, we with that said, we got our MAP of 0.9. So let's take this right now. And let's just plot some examples and see what it looks like. Okay, so that was bad. Bad. What? This is horrible. Yeah, so of course we need to load the model. That makes sense. So there's the cat, and you know, this is not a perfect bounding box, but I think the IOU is greater than 0.5. So according to MAP, this is correct. This is also correct. I guess this is correct as well for the, I'm not really sure what the target should be here, but we can see there's a person in the back and there's a horse right there. Then 2 persons, not perfect bounding box, but again, greater than 0.5 IOU. There's a train, and this one was a little bit bad. So that's probably why we don't have MAP of 1, but we can see it covers this one, and I don't think it covers the person in the back. Then we get the cat and the person, and 2 persons, and also the TV. So it seems to be doing the right thing. Probably if we train it a little bit longer, it's probably going to get even better. Is there anything else to say? I'm going to remove these parts. I don't think they're that important, or they're just there for us checking that it's doing the right thing. Yeah, one thing I do want to say is that if you want to train this, I highly encourage that you take a pre-trained model. So let's take ResNet, for example. So replace darknet with ResNet. You know, that would operate, or that would be functional on 224 by 224. So just resize to that. Actually, I trained on that for a little bit, and I did get pretty decent results even on using 224. I think I got it up to at least 40 MAP on the test set. YOLO originally got 57 on the test set. But so, you know, those are definitely some things to try out. And if you're also interested in training on this, then go ahead. I think implementing data augmentation, though, is very important, and pre-training is very important. So those are 2 things you got to do. And I think if you do those, then you're going to get a lot better performance. All right, this was a long video, you know, this took a lot of time to do. I'm hoping that these more advanced videos is something that you guys also think is useful. Yeah, if you guys want more advanced videos, I'll focus on doing more advanced videos. All right, so I just want to say thank you so much for watching the video. If you have any feedback, any things to improve, there was a large project, or probably many different parts that can definitely be improved, then do let me know, and I will try to improve it moving forward. See you. I hope to see you in the next video.